Hi friends, I'm Dr. Meenal and you're watching Meenal Ka channel. Welcome to my channel. Today we will try to understand that what is differential calculus and how the marginal analysis is closely related with mathematical technique differential calculus. For this we will start with the geometry of marginal analysis and then we will move forward to differential calculus. So let's start. Let's start with the geometry of marginal analysis. Let's assume a hypothetical total utility curve. As you can see on your screen, this curve indicates how the total utility will vary with consumers take of different amount of units of certain commodity. As you can see on x-axis, I have marked total units consumed, and on y-axis, I have mentioned utilities. Right. The average and the marginal utility can also be read off from this total utility curve geometrically. Let's see how. Uh, we take a point in this figure, we take a point P, right? On this point, consumption of OX1 units, okay? Right, on this point, how much is the consumption? Consumption is OX 1. This is the amount of consumption OX1, and with the consumption of this OX1 amount, the person is getting utility OY1. This is Y1, OY1. Okay, and what is this? This is the average utility per unit of consumption. You can calculate how. So average utility per unit of consumption, how much it will be? It will be OY1 OY1 upon OX1, right? What is this? This is the average utility per unit of consumption. What is average utility? Average utility is total amount of utility upon total consumption, right? So total consumption is OX1 and the total utility is OY1, so we can get the average utility. But you know, OY1 is equals to PX1. So this is PX1, right? So this OY1 is equals to PX1. So we can say average utility is equals to PX1 upon OX1. So this is average utility, or this ratio is called the slope of line OP, right? If we can draw a line from point O, this is the point O, and this is curve, right? This is curve, and if we can draw a straight line from O to P, okay, this is the straight line from O to P, then what is slope? Slope is equals to y upon x. This is from geometry. Slope is always equals to y upon x. So slope of line OP will be equals to px1 upon ox1. That means average utility is, this is the slope of line OP, and if this angle, we denote this angle by alpha, then trigonometrically it is tan alpha. Slope of line is equals to y upon x, and also this is equals to tan and the particular angle which the line is making from origin, right? So for example, we write it beta. Okay, so this is 10 alpha. So average utility, what will be the average utility? Average utility is the ratio of the lines px1 upon ox1, or the slope of the line op, that means slope of the line starting from origin to the point P, and trigonometrically we say that this is equals to 10 alpha, where what is alpha? Alpha is the angle POX1, or it is similar to PRQ, right? So this is the angle. Okay. What is the value of marginal utility? This we have calculated average utility geometrically. Now come to the point that what is the value of marginal utility? We know the average utility at point P, which is given by the slope of line OP, join of origin with this point, that is 10 alpha. This we have calculated. The marginal utility, what is marginal utility? It is at the point is given by the straight line which is tangent to the curve T. Like, okay, right? If we draw a straight line, if like this is a straight line T1, okay, the line T1 tangent T dash, okay, this line T, and this is T dash. So line T dash, tangent T dash, and slope of that line is the marginal utility, right? Slope of T is what? It is marginal utility. Okay, that means marginal utility at any point is given by the slope of the tangent to the curve at the point. And if this angle is theta, and this is theta, if this angle is theta, then this is equals to what? This is equals to 10 theta. That means if you want to calculate marginal utility at any point, if you want to calculate geometrically, then what you have to do? You have to draw a tangent on that line, and then you have to join the tangent to the axis and the 10 theta, and the angle made by that line with the axis 10 theta of that angle will be the slope. Or what you have to do, you have to calculate the ratio. That means in this case, if we are calculating the tangent, the ratio px1 upon tx1 will be the marginal utility, right? That means this is equals to px1 upon tx1 will be the marginal utility. Yes, of course, y upon x. This is y upon x at that point. This is the marginal utility. And this is not only true for marginal utility, but is also true for marginal product, marginal cost, marginal revenue, etc. When these are to be found out from their total curves. At any point on a curve representing total y, the marginal y can be found by evaluating the slope of the tangent to the curve at that point, right? Now we move to the differential calculus. First, look at this. Look it on your screen. This is the definition of differential or a derivative. Suppose f is a real valued function and a is a point in its domain of definition. The derivative of a at a is defined by limit h tends to 0 f parenthesis a plus h minus f parenthesis a upon h. where limit h tends to 0, provided this limit exists. Derivative of fx at a is denoted by f prime a. This we have discussed earlier in another video, that there are so many types of major four types of notation for derivatives. So you can watch that video for if you want to know about the notations and you want to understand that where you should which notation. So observe that a prime f prime a quantifies the change in the f prime x at a with respect to x, right? You now let's understand this definition. Let's go to that previous figure. Hmm. Let's now translate the marginal concept we have defined in the form of slope or in terms of derivative. Suppose we denote small increase in the consumption x1, x2, right? This is x1 and x2. Suppose this is the small increase in the consumption from x1 to x2. Remember, this is a small increase only, and we can denote this by delta x, right? This changes total utility by a small amount. How much? This is this y1, y2, right? So this is y1, y2, and we can denote this by delta y. Okay. Therefore, the change in the utility per unit will be, how much will be the change per unit? It will be y1 upon y2, change in total utility upon change in consumption x1 upon x2, right? We can denote this as delta y upon delta x. Okay, and we can write this as we can add y and we can subtract one y from this equation, from this term, right? And but what, y is equals to fx, right? Y is function of fx, and so y plus delta y will be equals to f x plus delta x. So let's put these values in this. So we get this will be equals to f x plus delta x minus f x upon delta x, right? Just see that this is nothing but this is the slope of line PR. Okay, if this PR is line, then this is nothing but this is the slope of line PR, because this is what, this is delta y, right? RQ is delta y, and PR, what is PR? PR is delta x. So this is the slope of line PR, right? And it depends upon the value of delta x, right? Uh, but line PR is not tangent to the curve at R, right? This is not tangent to the curve at R. So what can we do? However, if P approaches R on the curve, PR shift and coincide with QR. PR will become tangent to the curve at R and will measure rate of the change of Y with respect to x. That means if I hope it is clear to you. That means if t approaches to r, or we can say if the p tends to r, then it will be it will become tangent, or we can say if this delta x limit approaches to 0, right? If this delta x approaches to 0, this p will approach to r, and this line pr will be tangent to the curve total utility. So if we take limit of this function, and we say if the limit of this function's limit delta x tends to 0, then it will become tangent to the curve total utility. This is fx plus delta x minus fx upon delta x, right? So that means it will become tangent to total utility, and that means it will be marginal utility of that curve at point P or R, whatever, because delta x is tends to 0, so PR will be a point, right? So, and this is what? This is delta y upon delta x, and in differentiation, how do we write this? We write this as dy by dx. Okay, we had seen in our definition of differentiation that this is the definition of differentiation. In our analysis, we have taken delta x over here instead of h, and this is because in this we have written that there is minute change in a, that is a plus h, and in that analysis we had taken x plus delta x, and this is x. So what is this? This is the differentiation of function y with respect to x. And one thing you should remember, always remember that dy by dx is doesn't mean that dy is divided by dx, right? It doesn't mean that dy is divided by dx as it is appears to be, right? In fact, dy and dx have no separate identities. It is a notation only, and with this notation, you have to always keep in mind that this notation means this division, right? This division, where limit of this division is delta x tends to 0, right? This is a notation. This is not a fraction. This doesn't mean that dy is dividing dx. This means this division, right? It is just a notation which saves our time in writing the whole expression. The limit to which the ratio delta y and delta x tends with delta x approaches 0. Okay, so thanks for watching my video. Hope you understood everything about differentiation, that what is differentiation, and how geometrically we find out the marginal and average concept from the total concept, and how the differentiation is related to marginal concept. So thanks for watching. Stay tuned and